So as he mentioned, and thank you for coming, everyone. So I'm Erik Jansson. I'm a senior graphics programmer at Remedy Entertainment. This is a talk on the GPU-driven rendering pipeline that we made for Alan Wake 2, featuring mesh shaders. So let's talk a bit about this talk's agenda first. So I'll be starting with an introduction about Remedy, about our Northlight engine, and also about our previous games that we've made, because we need to talk about how the technology looked like back then. This was a non-GPU-driven rendering pipeline, so we need to understand the problems back then to see why we needed to make a GPU-driven rendering pipeline in the first place. So we'll start by talking about our GPU-driven rendering pipeline, its architecture, and what things you need to think about when making your own. We'll then talk about meshlets, and we need to talk about meshlets because this is the new primitive that you use to render using mesh shaders. And because we have a lot of meshlets in our game, we need to be able to call them. And finally, we'll get to the star of the show, which is to talk about mesh shaders. And then I'll wrap up with some thoughts and what I think is next when it comes to GPU-driven rendering. So if you've not played Alan Wake 2, I'm going to show a short trailer of the game here to get an idea of what we're getting ourselves into. So enjoy.
The killer left the heart next to the body. This wasn't some random act of violence. This was a ritual. A page of text written with a typewriter. Someone's been watching us.
How do you run from an idea? From a story that lives in your head? I need to escape this nightmare.
Wake says the story will change reality around us. Written into the story. I brought you the Heart Witch. Show me the terror.
Show me the terror.
Awesome. Let's start with some introductions. So I hope you've heard about Remedy, but if you haven't, we've been in the industry for almost 30 years. Actually, next year we'll be celebrating 30 years in the industry. Our main headquarters is in Finland, but nowadays we also have a satellite studio in Sweden. We're almost 400 employees by this point, and we use our own custom engine called Northlight. Northlight is our engine and editor toolset, and it has just the right features for our games. So it's kind of very focused type of engine. Northlight is also a team. We were around 60 engineers and QA, so we've been grown quite a while. Just a couple years ago, we were around 40. And we've been working on Northlight for quite a while, ever since Quantum Break, so 2016. The most recent development is that we've been moving over to a USD, so a Universal Scene Description format. This didn't happen for Alan Wake 2, but it is coming for our future games. But probably you know Remedy mostly from our games. So classics like Max Payne, Alan Wake, Quantum Break, Control, and of course Alan Wake 2. For this presentation, I'll be talking a little bit about Control, because that's before the GPU-driven rendering pipeline, so we can see, kind of compare it against the technology in Alan Wake 2. And then, of course, we'll be talking about Alan Wake 2. So let's start with Control. So Control was released for the previous generation consoles, then ported to the next generation consoles, the current generation consoles, rather. It featured ray tracing, 60 FPS, and quite fast loading times. If you haven't played Control, it's mostly set indoors, featuring brutalistic architecture. So lighting quality is very, very important in this kind of scenario. There's like very flat geometry in this game, which makes it nice for ray tracing, of course, and also very nice for culling. Like it's very easy to identify occluders in this game. Here's a screenshot from one of the areas in the game. This is the research sector. As you can see, very divided rooms and nice flat geometry. This particular scene is around 3 million triangles after CPU side culling. Even then, it's quite CPU heavy. We use Umbra 3 for the culling here. And maybe worst of all, on previous generation consoles, we were using quite a few cores to record command lists, so not very, very efficient. For Alan Wake 2, we knew this wasn't going to be enough. And we knew already back then that we were only going to be targeting the then next generation consoles. An asterisk here is that all the performance data you'll be seeing, that I'll be presenting here is from an Xbox Series X. Thank you very much to Xbox and Microsoft for allowing us to show console numbers. It allows a bit more representative performance numbers compared to PC. If you've not played Alan Wake 2, it's a semi-open world game set in hub locations. It's set in 2 different locations, a Nightmare in New York and a Pacific Northwest. The Pacific Northwest is the one we'll be talking about today, because that's way harder to render. It features very dense vegetation, and photogrammetry is used pretty much everywhere. So everything from like tiny rocks to like branches are all photogrammetry scanned, so lots of triangles. This is kind of a regular scene in the game. We'll be looking at this one quite a few times, and you can already see the geometric complexity has increased compared to Control here. That particular scene we just looked at has around 200 million triangles before doing any kind of culling. And worst of all, there's no really main occluder. There are no walls here. Like a tree could be an occluder, anything could be an occluder. And graphics programmers' worst nightmare besides transparency is alpha testing, and we have a lot of that here. And this is where the GPU-driven rendering comes to the rescue. It features lower CPU overhead, fewer commands for us to record on the CPU side, and best of all, actually the render thread is just 1 core, so it leaves a lot of CPU time for other stuff. After GPU side culling, that scene is just 10.6 million triangles, so a lot more manageable. So this talk will essentially be the journey. How did we get from 200 million triangles to 10.6 and make it run in real time on the consoles? So let's start by talking about the GPU-driven rendering, because that's really the glue that holds all of this together. Let's first look at the architecture. So unfortunately, every GPU-driven render needs to start on the CPU at some point. In our case, this starts when an object inserts draw calls, and I put this in quotes because it's not really a draw call, into something that we call a draw set. This is a persistent object, so this is not removed in between frames. So it's only when the object is streamed in or out. These are then filtered into something we call buckets, and these are based on materials. So for instance, the bucket here in the middle is where we would insert our vegetation, because it's alpha tested and it needs to go through the depth pass. And the bucket to the left is where we would insert our rocks and stuff, which is like single-sided and not alpha tested. But this is kind of still an abstract concept. For the GPU side culling, we need to instantiate this into something which we call a visible draw set. And this encodes it per view. So for instance, one of these draw sets will be per the camera, and one of these might be for a shadow map, for instance, for a spotlight. This structure holds all information that we actually need for doing the GPU side culling. The CPU constantly pokes the GPU with updated information, for instance, if there's been any changes to the loading, or if any meshlets have changed, for instance. But we only update the differences. We never do a full update. And that's pretty much everything that we actually do on the CPU. Everything else is done entirely on the GPU. What we're interested in talking about in this talk here are the geometry passes. And these are the main ones we have. So we have a skinning pass, followed by a depth pre-pass, followed by shadow maps, and then gbuffer. And this is a 2-pass approach. So the gbuffer pass, we don't really need to render depth there anymore, so we render using depth equal. The depth pre-pass is the one that has already rendered the depth here. And these are the 2 passes, the ones which do depth, that we'll be looking at most, because those are the hardest ones to render, because they have alpha testing, right? For the gbuffer, we don't really need to do alpha testing anymore. We have already rendered the depth. And these 2 are special because they feature something which we call a 2-pass occlusion culling system. We will get to actually occlusion culling a bit later, but it's important to already talk about this thing. So occlusion culling is the kind of the classic chicken or egg problem. You need to get a hierarchical Z buffer to do culling, and you want to do culling because you don't want to render anything, but you need to render things to do occlusion culling. So how do we solve this? And there are many ways to do this, but the way we have chosen to do this is to render the last frame's occluders, build a hierarchical Z buffer from that, and then do the culling. This, of course, leaves gaps in the geometry, so that's not very good. So we need to render the remainders after this. But I find that this is a bit hard to kind of visualize, so let me show an example of how this works. So this is the easiest way I could come up with. So I spin the camera really fast. I take a capture, and then look at the depth. And this is us rendering the previous geometry. And if you look here to the left, you'll see that there was some geometry missing, and then when we render the remainder, it gets completed. That's what this is. And this, after the culling, all of this information is then passed towards the next frame, and then the cycle continues, or rather, the cycle is complete. The tracking we do is done per meshlet, and we do it using a bit field. As you can imagine, this can become quite big, but in general, it's not super bad. It's around 56 megabytes, I think, for a pretty complicated scene. Something else that you'll have to think about when making your own GPU-driven render is bindless. The general idea with bindless is that you don't really want to do individual bindings. You want to index directly into a descriptor heap. This leads to lower CPU overhead because you don't really need to bind individual slots. And it's also more flexible. You can reuse the same pipeline. I think we have like maybe 3 or 4 pipelines in our render, so it's quite lightweight. We already had bindless textures due to control featuring ray tracing, but we still had to do some work for Alan Wake 2. Something you will very quickly run into if you're doing bindless is DXC complaining about divergent resource access. To fix this, you can add a non-uniform resource index around it. And this pleases the compiler, so it will stop complaining at you. But be aware that this can have a potential performance overhead, especially on AMD GPUs. You can usually see this if you put this in AMD RGA and notice the extra loop that happens. It will usually be followed by like a label and a read operation, wave read operation. You can also convince DXC that the index is uniform by doing a wave read lane first, for example. But be sure that the index is actually uniform. Don't trick the compiler here, because otherwise you're going to get artifacts. So the part we had to do for Alan Wake 2 that's more than bindless textures is bindless geometry. All of our meshlets are done using bindless. So on topic of meshlets, let's actually talk a bit about meshlets. This is the new primitive that you need to be able to render using mesh shaders. So how do you generate them? And this is actually very simple. You just use a library. We use the excellent library by Arseny Kapulkin. It worked pretty much out of the box for us. There are a few edge cases here and there, like for instance, because this is a greedy algorithm, it might forget some of, or it might like drop some of the triangles into something that's a bit further, which might produce a bit worse bounds. But other than that, it's very good. There are very few edge cases we had to fix manually. And you just need to call these 2 functions on your polysoup. Here's an example from Intel Sponza, and here are the meshlets. One question you will have to answer here is, what's the mesh size? Well, rather, one of the things you need to pass into Mesh Optimizer is the meshlet size. For Alan Wake 2, we chose 64 triangles and 64 vertices. This is a very tricky optimization problem, by the way, because if you make this, increase the number of triangles, in some GPU architectures you get more efficient rendering, especially in synthetic test scenes. But for smaller triangles, you get better culling efficiency, right? The meshlets are going to be smaller. For us, this was the right trade-off, but for other games, it might be different. So for your games, be sure to try out and just don't take these numbers to heart. Yeah, the real thing here is try it on your game and see how it performs in a production scenario, not in a synthetic test scene. We also use something called cone culling, and we provide a weight. I'll talk about this cone culling in a bit. So now you have your meshlets. Something else you will need are the bounds. You need this for doing culling. This you can also just do using a mesh optimizer, so that's pretty simple. And you have a bounding sphere and a normal cone. The normal cone, you can think of it as kind of the general direction the meshlet is pointing at. It's like a direction and the spread of the normals. Here's an example from Intel Sponza, and here's how the bounding spheres of Sponza look like. The bounding sphere symbol is just the center and the radius using full precision. The normal cones is a bit trickier. That's the axis, so that's the direction the meshlet is pointing at, and the cutoff is the spread. And this is a quantized value, so you need to dequantize it on shader side, but it's very compact. That's just a single uint if you pack it right. So that's for generating static geometry. Now, how about dynamic geometry? And even worse, all of our vegetation is skinned in Alan Wake 2. You can go and watch the GDC presentation earlier this year to learn more about that. But how about the bounds of this? Like, if all the vegetation is skinned, how do you update the meshlet bounds? And this is how we did it. We just have a compute shader that runs over all the skinned meshlet instances. For the bounding sphere, it's just a wave active min and max on the vertex position. You can then figure out the center and radius pretty easily from that. For the normal cones, it's a bit trickier, but it's kind of the same idea. Wave min max on the vertex normals, and you can figure out the cone axis, so kind of the average direction. You can then get the spread, so the cutoff, by using the axis and getting kind of the dot product between the axis and each vertex normal, and getting the smallest number from that, and that gets you the cutoff. This is how long this takes on Series X, a bit under 0.2 milliseconds for updating bounding spheres, and 0.1 milliseconds more for the normal cones. And this is in a pretty, an area with quite a lot of meshlets, so this is actually pretty good. And this is the area I showed before, and these are the meshlets of it. These black areas here are height fields. These also use mesh shaders, but these are not visualized here. As you can see, everything from skin geometry to trees that's also our skin all have meshlets. I think this is actually a bit easier to see in motion. So I'll show a video here, and I'll turn on the meshlet visualization here in a bit. You can see some popping, and this happens because we don't have hierarchical loading yet. We just have simplygon loading. But usually the popping isn't super apparent. But you can see that everything from vegetation to characters all have meshlets, and the bounds are updating in the background here as well. So with that many meshlets, the question comes, how do you draw them? And you don't. You cull them. So let's talk a bit about culling. So in that scene there, we had around 200,000 instances, 4 million meshlets, and 200 million triangles. You could naively try to render this, and we'll be looking at a few tables here, so we can maybe try to understand what these are. So the left part here, the text, says what type of culling we're using. In this case, no culling. The left table is how many triangles we're rendering, and the right one is how much time each pass took. We can see here, let me just check the notes, 173 million combined triangles. There's some filtering happening in the buckets. That's why we went from 200 to 173 million. And that's 42.4 milliseconds just for shadow for the G-buffer pass. We obviously cannot ship a game that's going to run at 30 FPS with that kind of stuff, so we need to think of something. So I'll present now the culling pipeline which we used. And this is actually very simple. We have meshes, which are actually mesh bounding spheres, which we do for culling. We then do frustum culling, contribution culling, which is kind of culling small objects on the screen, occlusion culling, which is culling objects behind other objects, and that's it. That's the visible meshes. And if this was the vertex shader pipeline, we would be done here. But since we are using mesh shaders, we can continue and do more culling. We do this by using, so this is all a compute shader, and this then follows by an execute indirect into another compute shader, and then we start culling meshlets. And we do the same things here. It's also just bounding spheres. Frustum culling, contribution culling, and special to the meshlets, normal cone culling. It doesn't really make sense to do normal cone culling for meshes, because the normals will be kind of all over the place, so you're not really going to do any kind of culling. And finally, occlusion culling. And this is the final set of meshlets. This is what we pass on to the mesh shader, also through execute indirect. So let's go through each type of culling. So frustum culling, I'm sure everyone knows about. You just have a bounding sphere, and you cull it against the clipping planes. And this could be anything, camera, spotlight. This is the code for it. I'll be showing some code throughout the presentation, but the idea here is that you don't really need to follow all of this. This is mostly as a backdrop and also for reference. When you come back to this presentation at some point, if you want to implement it, you can use this as kind of a guiding principle of how to do it. The idea here is very simple. For each clipping plane, you get the sign distance field between the bounding sphere and the clip on the plane, and then check the distance between the bounding sphere radius. This clip plane count here in the loop is actually quite nice that it's flexible. In our case, it was useful because for each of the directional shadow map cascades, because the shadow maps run after the depth prepass, we know what the occluders are. So we can fit the cascade to the occluders in the camera. And this results in a frustum that's more than the usual amount of clipping planes, I think up to 13 or something like that. But it results in a much better fit for the cascade frustums for directional lights. And this is already hugely helpful. We are already kind of in 30 FPS shippable territory, maybe. So this is a reduction of 31.8 milliseconds. This takes a total of 10.6 milliseconds, and we're just I put in quotes, 25 million triangles. So that's pretty good. But we can do better. So contribution culling. Cull small bounding spheres on the screen is the idea here. The algorithm is pretty simple. You take the bounding sphere, project it onto the screen, and you will essentially get a LBRT, so essentially like a screen projected rectangle. And this LBRT means left, bottom, right, top. You then get the width and the height of this rectangle, and then you compare it against the minimum contribution. And this minimum contribution is just artist-tuned or engineer-tuned, if you will. This sphere screen extends. There's a very efficient implementation by Arco, which you can find online. Highly recommended. We actually only do this contribution culling for shadow maps pass. The LODs have already been optimized for the main camera, so the triangle is already kind of in the right size. But for the shadow maps, these triangles can be quite small, and as we all know, rasterizing small triangles is a bad idea. So yeah, we do this for the shadow maps. It can be a bit tricky to tune this minimum contribution actually for the meshlets because they're kind of uniform in size. So I'd recommend actually splitting this into mesh contribution and meshlet contribution for your game. We didn't do it, but I recommend that you do it because that is a better idea. This isn't actually super helpful in this case. It just saves 0.2 milliseconds only for the shadow maps pass. But there is an area, if you continue down here, where it saves around it saves 2 milliseconds. We call this area, like the further away here, the Swamp of Doom, which is a really bad location with a lot of shadow casters. For the meshlets exclusively, we have something called normal cone culling. It's kind of like a coarse backface culling for meshlets. And yet it consists of an axis, which is the average direction, a cutoff, which is the maximum angular spread, and the apex, which is the position. Orthogonal projection is pretty easy. So for instance, for sunlight, that's just a dot product between the view and the cone axis. And then you compare it against the cutoff, which is the spread. Perspective is a bit trickier, but it's kind of the same idea. You just need to consider the apex as well. In our case, because this is quantized, you need to dequantize it first before using it. In the end, we actually did not use normal cone culling in Alan Wake 2. There were a couple of reasons, but the main reason is that the occlusion culling is so precise, it already kind of calls the back faces. Kind of if you picture a sphere in front of you, and you picture you doing occlusion culling with meshlets, you're going to see that most of the meshlets on the backside are already going to be called. But this could be worthwhile for some other games where the occlusion culling isn't as precise. This helps quite a bit. That's 0.5 milliseconds faster. And then we come to the holy grail of culling, which is occlusion culling, which is to cull small objects behind other objects. For this, you use something called the hierarchical Z buffer. You can kind of use this for doing depth queries. And this is the code for it. But this is a bit tricky, so let's break it down bit by bit. You start by taking the bounding sphere, or the bounding sphere rectangle, getting the UV coordinates, so essentially you get the UV corners of this object. You then compute extents, so how wide it is in pixels, and then you get the MIP level from that. And this just uses your regular MIP calculation. Using these UV corners and the MIP level, you can sample the occlusion depth, and you get essentially 4 depth samples, right? 1 for each UV corner. You then get the biggest of them, and then you compare it against the bounding sphere. And that's it. You can improve the results even more by trying to sample 1 MIP lower if the texel footprint is less than 2 pixels. This results in better occlusion culling. It does mean that you need to have a very conservative hierarchical Z buffer, though, for this to work. We actually fought with this for quite a while. Otherwise, you're going to get lots of flickering in your game. So how do you build a good hierarchical Z buffer? Let's talk a bit about that. The general idea here is to take a depth buffer and do a max downsampling and then produce MIPs from that. This is how it looks like. So the same usual scene. This is the depth visualized as a heat map, and this is how each MIP level looks like. In our case, we used a single pass downsampler, not unlike AMD's SPD. Something you need to think about is that you need to do it on a max operator and not average. And you also might have to pad the depth buffer to a power of 2 to make sure that the results are actually conservative, or handle the edge case yourself. Better alternative on consoles is to use something called the high Z. There's actually a reference by, I believe Graham Willidahl did it some years ago. But SPD is still pretty fast, just takes 50 microseconds. So we use SPD in our case. And this is hugely helpful. This is 2.2 milliseconds less rendering time, and we're down to 12.3 million triangles here. This is it in action. So here is, I freeze the camera, and you can see the glorious frustum culling. But that's not super interesting. So let's check occlusion culling. So I'm using Saga here as an occluder, and you can see Thornton there. And I freeze the camera, and you can see that he's gone, and so is the vegetation behind him. Of course, the best kind of occluder is the wall, so and we have plenty of those, especially in the New York part of the game. Pretty cool. So now that we've learned how to cull it, let's also learn how to draw them. And for this, we use mesh shaders. So this is your usual old, in quotes here, old graphics pipeline with lots of optional stages in the middle. You really should not use a geometry shader, by the way, maybe for some debug stuff, but please don't use a geometry shader. It's usually very slow. Just a side note. And this is the more modern graphics pipeline. I call it modern here because this is usually a bit closer to what the hardware is actually doing nowadays. In our case, we only use a mesh shader. We actually don't use amplification shaders at all. So this is what we'll be talking about here. I was thinking actually how to explain mesh shaders, and I was thinking figures, and I was thinking bullet points, but I think the best way is to just show our mesh shader. Mesh shaders are anyway not supposed to be very long programs, so let me just show it to you. It's something like 50 or 60 lines of code, and we'll go through it bit by bit. So this is the beginning of a mesh shader. This is a depth mesh shader. You can kind of see it kind of looks like a compute shader. If you look here, it just has a number of threads, 64 in this case, and we're outputting triangles. Something else that's special are these two things here. So the output indices, so this is something that you need to form a triangle. And we output maximum of 64. And we also output vertices. These are the vertex attributes that go into our pixel shader later. I'll show what this thing is in a bit. We then do some bookkeeping. We figure out how many meshlets we're going to draw and what index. This is that depth process vertex output thing, and you can see that we have the position here, we have draw index, and we have attributes. In our case, this attributes is just UV coordinates, because this is just going to draw alpha-tested stuff, and this is just depth. So this is really one of the simplest mesh shaders you can make. We then do some meshlet culling. You really shouldn't be doing meshlet culling actually in the mesh shader, but we did it anyway. I recommend that you don't. Instead, do like a compaction step in a compute shader before, but we did it out of convenience. We need this to be able, since someone might have removed the draw in between frames, and because we need to draw the previous geometry before doing any culling, we need to do this. We also call based on the lodding, so essentially if the LOD is not the same, we need to throw it away. But yeah, don't do this. Do a compaction step instead. That's better. We then start to get into the interesting things. Here we have the meshlet header, and we read how many vertices and how many triangles we're going to be outputting. And then we just set that to the mesh shader. Now we start outputting the vertex attributes. This is some bookkeeping. You don't really need to check this. Here is where we do the vertex transformation. And I'll come to this in a bit. And this just writes it out to the mesh shader. So that depth vertex attribute is just a texture coordinate, and that process vertex just transforms the position to the right coordinate system, and it just gets the UVs. So pretty simple. And last but not least, we output the triangles. And that's it. That's our mesh shader, at least one of the simplest mesh shader we have. And here's a comparison between vertex shader and mesh shaders. This is on a PC, and we have unfortunately thrown away the Xbox Series X vertex shader implementation, so I just have this on PC. But you can see that in some cases it's even 2 times faster, almost 2 times faster. This is not precisely because the mesh shader is faster. It's more to do that it's so much more precise at culling. You can cull meshlets instead of entire meshes. That's kind of maybe the key takeaway here. There is something that you can do in a mesh shader, though, which you cannot do in a regular vertex shader, well, besides the better culling, and that is per primitive culling. So yeah, it's possible to do even more culling besides the culling which we have already done in a mesh shader. And this is something called per primitive or per triangle culling. You can do backface, zero area, essentially anything that you could do in a soft triangle rasterizer. This is an example of the small primitive filter culling. I'll not really go over all of this. The idea here is that if a triangle, rectangle, doesn't straddle any of the sample points in a pixel shader, we can throw it away. All you need to do is take this B triangle called and pass this into the SV called primitive. We tried rolling our own compaction code, but that wasn't really performant on PC or Xbox. You can do this if you, in some special cases, and get a performance win, but I'd recommend that you don't. It's usually more work than it's worth. But the basic idea is that you use wave intrinsics and then share the attributes using LDS is kind of the general idea around it. We also kind of got mixed results on PC, like on NVIDIA hardware, this is a performance loss in our case. On RDNA 3, this was a wash. On RDNA 2, this was a huge performance win for some reason, 1.8 milliseconds faster. On Xbox, though, pretty nice performance win, 0.8 milliseconds on the Series X, and on the Series S, 1.67 milliseconds, so definitely worth it. And this is where we get the final number, 10.6 million triangles, down from 200 million. So let's start talking about some of the conclusions from implementing all of this. So a quick summary. So we successfully shipped a game that uses mesh shaders. It's actually one of the first games that shipped with mesh shaders. I think the other ones are Avatar, and also some UE5 titles shipped with mesh shaders. We also moved Northlight to be a fully GPU-driven rendering engine. This makes it a lot more flexible. Usually, it's artists complaining to us about things being slow. Now we can complain to the artist saying that your content is slow for some reason, so it's a lot better to do that, at least as a graphics programmer. I'm sure the artists feel different. And kind of on the grander scheme, I'd say that mesh shaders are quite mature technology as of today. It certainly was not the case like when we started this out, but IHVs have been very good at fixing bugs and like have been very helpful. So I think if you try mesh shaders today, you'll be quite pleased with the results. They feature improved performance and flexibility over the old pipeline. The consoles also benefit greatly from low-level optimizations. Unfortunately, I can't really show those here, but if you are a console developer, feel free to reach out to us. We're happy to share some more details about this. And I think that, though I think the most important part out of all of this is that the meshlets are a surprisingly powerful new primitive to do culling on. It's incredible how much culling you can actually do using well-built meshlets. One problem with meshlets is that you need to produce them, but luckily there are plenty of good open source libraries for this, and also a lot of very good learning resources. There are actually 2 presentations tomorrow about mesh shaders, so be sure to check those out, and one of them is even about work graphs. Extra cool. Also, graphics debugging tools have actually gotten very good at this. There were also issues in the beginning, but I think all of the issues that we had at least have been fixed. So this leads us into what do I think is next. This is maybe a bit into the future, but work graphs are definitely an interesting thing and something we are interested in. One of the kind of immediate things which it would help us with is that currently in the culling passes, when we do execute indirect, we don't actually know how much geometry we are outputting, so we need to do a worst-case allocation, and those buffers can become quite big. With work graphs, you don't really need to do that, so you don't get this kind of bloat due to worst-case allocation. Something else that would be interesting is a micropoly software rasterizer, kind of like a nanite-style approach. We do contribution culling, we do per triangle culling, but there are still cases where we need to rasterize small triangles. So yeah, some kind of classification step followed by compute shader. So kind of classification step needed to kind of classify, should we do the software rasterizer or should we do the just a regular GPU kind of fixed function pipeline? Something else which we did try in Alan Wake, but I think we didn't fully test this because I do think this would be a big win, is to sort the draw calls to reduce overdraw from alpha testing. This is very expensive, by the way. All kinds of alpha testing is super expensive due to overdraw. So anything you can do to help that with, I'd recommend you try it, especially if you have a lot of vegetation like we do. Something else which would be interesting would be seamless meshlet loading. Our loads are pretty good, but there are still some cases where they pop, so some more seamless meshlet loading would be nice. And the final topic here is kind of more a research topic, meshlet compression. Some people have been able to get it down to just 5 bits per triangle, which is pretty impressive. But yeah, remains to be seen about performance and so on, but this is definitely something we are interested in looking at. And that's it. I'd like to thank some people before finishing off here. There have been many developer technology engineers that have helped us ship this game, and I'd like to thank all of them. We would not have been able to ship the game in the technical quality without their help. Some of them are even sitting here today, I believe. I'd also like to thank the team back home. This is the wonderful rendering team we have at Remedy. While I'm the one presenting here, this is really the combined work of everyone there. I'd especially like to thank Tato Alto, my lead, who did a lot of the work for the GPU-driven rendering pipeline. He will actually be giving a talk next month, I believe, at REACT, the Rendering Engine Architecture Conference. It's online, so be sure to sign that up if you want to learn even more about GPU-driven rendering. And that's it. Thank you very much. And I believe we have some time for questions. Peter?
Sorry, if you have questions, there's the microphone in the middle of the corridor, so you can use that.
Thank you so much for your talk. I have two questions. So one, I didn't really understand about using the last frame result to cull. Are you using like the last frame depth buffer, basically? And if yes, how do you solve the issues when something is animated or when the camera moves? Because apparently, like, you can potentially have something that was not visible become visible.
Yeah. So we do it unlike. I believe Unreal Engine, they do some kind of reprojection of the previous depth. We redraw the geometry. So essentially, we know from the previous frame what was called, and we essentially have the indices to those meshlets. So we redraw those. And this means that the geometry we draw is always going to be correct because it's in the new camera view, but it's the same geometry. That's why we need to fill in the holes also.
Oh, okay. So that works also with animated geometry because you draw them with a new animation.
Correct, correct. And because the skinning happens before that as well. Yeah.
And second question, you mentioned that there was basically like per meshlet culling.
Yep.
And I wonder why does it outperform in the end version on vertex shader? Because you can, when you cull the whole meshlets, you can just cull them anyway. Like, you don't need mesh shaders. You can like still cull them like they were culled before in the GPU-driven pipelines before the meshlets.
So yeah, the question here, I guess, was that you can still divide it into meshlets and still draw them using vertex shaders, I guess is the idea. Yeah. We didn't really go with that approach, but I understand the idea, and you could probably get closer to the performance there. I think we tried this at some point. There was quite a bit of wins, but it still wasn't quite able to match the mesh shader performance, maybe because of the per triangle culling.
No, I mean, per triangle culling, I get it, and you said it mostly works on consoles and specific AMD GPUs. The question was rather like specific meshlet culling, because I guess mesh shaders comes with some overhead, so it was I didn't understand fully like where this whole win come from, but I guess this is more meshlet culling versus non-meshlet culling.
Yes,
version.
I guess, yes,
Right.
correct. Yeah, that's just the way we've implemented the vertex shader path and the mesh shader path. You could probably do kind of per meshlet culling on vertex shaders as well, kind of, and you could probably get better performance, but in our case, we wanted to have this kind of split, just made more technical sense for us.
Thank you very much again.
Thank you for the talk. So the first question is, you shown the frame structure, and you had shadow depth pass right after the pre-pass,
Yep.
before the G-buffer emission. So is there any specifics behind this?
Yes, so one of the things I showed there was the cascade fitting, right? And for the cascade fitting, we need to have rendered the occluders first. So we essentially get a list of the bounding spheres of what is visible, and we use those to fit the shadow maps for the directional lights, for instance.
Yeah, but you can do the shadow mapping after the base pass, and you will have information about cascade, about the fits.
Maybe let me go back to that slide. I think I know which one you mean. Let's see. Okay, it does not show up here. Well, that's fine. But yeah, there's the skinning pass, the depth pre-pass, the shadow maps path, and the G-buffer pass. So your idea here, or your question is rather, why can't we not flip them?
Yeah, like why not flip shadow pass and G-buffer? It's just out of curiosity.
No real reason. That's just how the frame is structured, I think. We could probably swap that out. Maybe that's actually worth trying. Let's see. There's definitely some question also about like what is the best way to do if you're doing some async work on the GPU, for instance. That's definitely true.
This is my follow-up question, basically. So I haven't touched mesh shaders myself, but the question on Ordinate 2 and 3. So having async in parallel with mesh shaders will give any benefits? Because we know that vertex shaders has low occupancy, but in case of mesh shaders, probably they will fill CU pretty much and async won't work.
Maybe. We actually don't do too much async. We probably should do more async than we are right now. One of the things we do use async for is ray tracing. So we do async like BVH build on the shadow maps pass, because that has generally quite low utilization. So that is definitely a good combination. Like ray tracing BVH build and shadow maps pass is a nice combo.
So mesh shaders pretty well like good friends with compute.
It's about the same, like vertex shader versus mesh shaders when it comes to the async work. We didn't experience any major changes to how that's structured for us.
Thank you for the answers.
Thank you.
Okay, so thank you, Erik, once again. Let's thank Erik with a round of applause.